All right. What's going on? 591. Let's get her going. Okay. All right. Let's talk about TFT or temporal fusion forecasting. All right. My name's Chris. I'm in your class. Cool. We're going to talk about the abstract, a little abstract introduction. Then we're going to go into model architecture. We're going to evaluate some of the performance of this. We're going to go into interpretability and the use cases, which are really cool. Look at that, and then we'll have a nice little conclusion. We'll wrap it off. All right, let's get to it. Cool. All right, so temporal fusion transformers for interpretable multi-horizon time series forecasting. Oh my gosh, what a mouthful. Anyway, so it's actually by a few researchers up here at the top, most of which are from Google and one from Oxford. Really cool. All right, so TFTs or temporal fusion transformers are a novel attention-based architecture combining high performance horizon forecasting with interpretable insights, temporal dynamics, attention-based DNA architecture for multi-horizon forecasting, achieving high performance while enabling new forms of interpretability. Oh my gosh, what a mouthful. So what this is it's a transformer for time series modeling. That's also wicked interpretable. And there's some really cool features to it where like you get this multi-horizon aspect where you can actually observe individual parts of the forecast at time. You get these prediction intervals, which are really great, useful. Yeah, it encodes stack covariates, which are kind of tricky too. Not all models can do that. Yeah, and part of the reason I love this model itself is the intervals. I mean, like okay, if you're talking about power, right? You're talking about the grid. It's great to know what the individual estimate is for usage at 2 in the morning, right? Or whatever, not two, whatever time you want to forecast. Um, and you might be really accurate, like 2 in the morning, normal day in the summer. You have a pretty good idea what your power usage is, but like, okay, 7:30 on a weekday in November in New England, where everyone could be using the power because it could be really cold when you have a storm going on, or it could actually be really nice. And there's a whole bunch of there's that variability. So creating intervals is really powerful, as opposed to traditional point forecast, which is like we're going to use X amount of terawatts at this time. Yeah. Okay. Okay. All right. Moving on. Okay. All right. So the architecture is really cool. So has static covariate encoders, which I just kind of talked about a little bit. Has a really cool gating mechanism, which and a variable selection part. It has sequence layers, and then temporal self attention. All right. And then what's also awesome about this, and we're going to break all these down, is it shows you your globally important variables, your persistent temporal patterns, and your significant events. Okay, cool. All right, let's get into the architecture. Let's get into the good stuff. Cool. All right, so what we really have here is encoder system where we're taking past inputs and predicting future inputs that are fed into the same system, right? We have an LSTM encoder here where we also feed in our static covariates. We have this gate. I'm gonna talk about that really a little bit more. We have a stack enrichment section, and then this is where we apply our self-attention and then our feed forward. And this is all in our temporal fusion decoder, which we're going to break down a little bit more. What we can see here is after our dense layers, we have our quantile forecast. So what it's doing is it's creating like intervals. There's what's happening. Yeah, and let's break this down a little bit further. Cool. All right, let's start with the gating mechanism. So because these are a really important part about this architecture. So really on a high level, what they're doing is they allow your model to skip unused parts of the architecture, which adds adaptability and complexity to help your models just generalize better to more data sets. So whatever you're seeing, it just helps it cater to a wide array of problems better. And these are really kind of the building block of this model. It's really important in how it learns. Something I thought was really interesting about this one is it actually like ELU and we have a GLU over down here. Sorry, which are kind of the math units of this. They're actually linear activation functions, which I thought was really interesting. Like there are non-linearities applied to more so towards the end, but I just thought it was really cool that like we're seeing linear activations where like because time series often really isn't linear. You know what I mean? Especially like A seasonal one is anything but linear, but it's really cool how they're able to add those in there and they work really well. Cool. And then we have the variable selection network. So also you can see these plots. That's like right here from the original architecture, just in case you didn't notice. Anyway, we have our variable selection networks. So what these are doing is they're helping us get insights into which variables are most significant and which aren't. They're applying GRNs and softmax, and they're helping us get our weights. So again, we have linear trans, and what we have a big part here is for our categorical variables, we're doing entity embeddings, and then for our continuous variables, again, we're doing linear transformations. And then each variable has its own GRN with weights shared across all time steps. Yeah, so basically this is how we're kind of inputting some of our variables, deciding the weights. Yeah, seeing how the model values what it wants to value. Cool. All right. Next is our static covariate encoders, which would be here. Cool. So what they do is they integrate information from static metadata using our GRN encoders to produce 4 different context vectors. And what these context vectors do is they wire into the temporal fusion decoder, which is this, which is really important for our processing. And there's really 3 specific contexts there's 4 vectors, but 3 specific areas, which is temporal variable selection, local processing, and enrichment of temporal features. Okay, so we're selecting them, we're processing them, and then we're trying to make them even better. Okay, and now we get into our interpretable multi-head, which is right here. Cool. All right, so this is where self-attention is applied. So what this does is it lets TFT learn this long-term relationships across different time sets. Okay, so really in general, there's we scale values V based on relationships K and queries Q, which makes up our attention formula here, where A is a normalization function, and N is the number of time steps being into attention layer. You don't see the N here. It's in a different one. There's actually a couple different attention formulas to this. And check out the paper if you're curious. Yeah. Yeah, anyway, and what this does is it just helps learn capacity. It gives other options to go through and sets to learn off of. And these different temporal patterns, common sets of input features, they're essentially what they act as are ensembles of weights into a matrix that keep your interpretability and just give you a better predictive power. Cool. All right, now we have the mean one, which is our TFDR temporal fusion decoder, which is kind of really the description of this whole block here. Okay, so there's four big parts of this, and what it's doing is it's using layers to learn relationships in the data set, right? Which you can kind of see with how it's broken down, right? Right, like we can see layers. Anyway, so we have our locality enhancement, our sequences, our LSTM. So we're identifying points of significance, anomalies, any changes in cyclical patterns. And what it does, it also handles these differences by feeding values from the encoder into the decoder. And this just creates a whole bunch of our features that we need for the decoder itself. What we're doing here in our stack enrichment layer is we're trying to enhance these layers. So what we're doing here is just kind of like it's doing its own feature engineering. If you're familiar with this, so like really kind of like giving you extra stuff, giving the model itself extra timestamps and dates to learn off of. And we have our self-attention layer, right? So what we're doing is we're grouping our features into a single matrix and doing multi-head attention. And this is cool because it's allowing a TFT to pick up these long-range dependencies that may be challenging for an RN to learn. Okay. Yeah, and then finally we have our position-wise feed-forward layer, which is now we finally have our nonlinear processing. So and I think that was really something that kind of blew my mind when I went through this, that like everything was linear up to this point, which is like, if we look, let's find it. Yeah, like you can see like it's right at the end. So like what's so cool is that like we can do these linear activation functions until we get to the very last section. And when we can include the nonlinearities, which I just thought was so cool. Maybe you don't, maybe you do. Hopefully you do. I hope you do. Cool. And then yeah, so this is where some of our gates come in, so we can skip some blocks. And again, this just helps with our and our prediction intervals come in here, which again is right here. Cool. Yeah. All right. I hope that made sense. Cool. All right. Now let's get into the why do we care? All right. So first off on our performance, just what we're doing here is we're training to minimize quantile loss function, which is just another loss function, but it's based on quantiles. So we're looking at, I think, the 10th, 50th, and the 90th quantile in this one. And then there's actually 4 different data sets used, being electricity, traffic, retail, and a volatility one. And it was trained for 6 hours on NVIDIA Tesla V100 GPU. And then the hyperparameters here are kind of listed. They didn't go into super detail, but we have some different parameters like our dropout rate, state, size of heads. You can read these for the different data sets. So this is kind of what they're looking to optimize. Cool. All right. Let's look at the performance. All right. So on average, TFT actually yielded a 7% lower 50th quantile and a 9% lower 90th quantile loss compared to the other models here. And we're really comparing against some really sophisticated models here. What you're seeing too in the brackets is like the percent increase, or sorry, the advantage that it has compared to these other methods, right? So I mean, we're 180% better than the REMA, and I mean, really, the Comtrans I really want electricity, but you can see that across the board, the TFT really blew everyone else out of the water, right? Yeah, so percentage in brackets reflect the increase in quantile loss versus TFT. Lower Q risk is better. If I didn't explain that very well, but yeah, like it's doing really, really well. All these different data sets, and compared to really a nice range. Like I like that we're seeing like a more statistical REMA, and we have our classic deep AR models, and then yeah, I don't know much about this one, but yeah, overall, really good performance. Because I wouldn't show it to you if it wasn't good, right? Yeah, all right. So this is probably, I think this is probably the coolest thing. So something too is like, not sure, not sure how much, if you have experience with like black box models, like you kind of notice, and if you don't, you don't. But like when you create these, right? Traditional black boxes, which are like most deep learning models, you don't really know what like exactly how they predict what they predict, right? Like you can't like when we've done all these models, we can't like plot a graph of our image classification. Like, oh, okay, it's looking at the ear on the dog, and that's or the nose is probably better. Nose on the dog, and that's the number one factor for how we separate from cats, right? Like it's not outputtable. And like for computer vision, like that's kind of part of the point. Like we want to avoid that, but when you're doing time series modeling, you really want to be able to like understand what it's predicting off, especially in like a business instance. Like it's a huge advantage, like even from the sense of like then you get to understand what's really driving it, right? Or let's go back to our power example earlier. Like, maybe the best thing it's predicting is not is like okay, is like the weather. Maybe that's what's learning off and saying, oh, okay, it's really more so looking at the seasonal patterns. Like we don't know, but so what's really cool is that there's these interpretability advantages that come to TFT. Finishing my little rant, where we can examine the points of each input variable in the prediction. We can visualize the temporal patterns, and then we can identify any regime or events that lead to a significant change in temporal dynamics. I'm going to break each of these down because they're really awesome. Okay, so and this is simple. I mean, like what TFT is able to do is able to output. Pardon me. Oh my gosh, like the weights for all the items. And like, I guess I don't exactly understand why this is so difficult with other black box models, but TFT sure makes it look so freaking easy. So I mean, like we can see exactly for the stat covariates, past inputs, and future inputs, the weights it's applying in all these different quantiles. So I mean, like, and this is our retail asset, right? So I mean, like, let's just take a look. Okay, like wow, like yeah, it's really valuing the item number for stat covariate. We can see how it's valuing like the month here is a really big factor, which is seasonal, right? The promotion, and something like this, like, well, like I like, and let's just say too, like it's picking up something that we don't want it to pick up, right? Like, a classic one is like if you ever do, I've done some business ones too, and if you put the name, right, if you put the name of something, you leave it in your training set. Eventually, it's going to kind of figure out that this one store this name is really predictive of great performance. So you always want to take that out. So if you saw that, obviously, oh, I made a silly mistake here, right? But anyways, this is really cool because it helps us understand our time dependent relationships, right? And it's cool because they can help us understand our seasonality, our business effects. Yeah, cool. And then when it also outputs our temporal patterns, right? So I think this is really cool too, where like we can see like this is like kind of our a very electricity data set. We can see this really classic. It's not like sinusoidal, but anyway, like we can really see these well and visualize them, and like you can totally like plot these too, like on your own. But it's great to see the ones that the model truly identifies. You know, where you're trying to see your responding variable on the top. And it's cool here on these two. It's just like the volatility data set. It didn't really pick up any temporal patterns, so we can just see it really evidently, and it's cool. Yeah, so you can see the spikes for electricity and traffic, weaker for retail. Yeah, so it learns these temporal patterns from the training data without hard coding. Yeah, it's really cool too, and this is awesome too. Like, and they talk about this in the paper, which I love. That yeah, like it helps you build trust, right? Like especially when you're like you need to understand like how this is working, and like it can be challenging in some instances to get uh like a business person to want to use a deep model, right? Because a lot of times you understand like these CEOs, it could have been there for 30, 40 years. So they've kind of been working off like Excel spreadsheets, and like their forecasts are good, but like they're comfortable with how they're done. So it's pretty tough to be like, no, no, no. The analyst or this data scientist or engineer, whoever's writing these models, knows they have a superior method. But the interpretability side and getting people to believe in it is actually very difficult, right? It's way harder than it should be. So having this ability to show people and work with them is awesome. Yeah, and it's cool because yeah, and it also and then too maybe you see something like and it's kind of this specific feature engineering probably ties a little bit more into the last slide, but maybe there's something like, you know what, it's not really picking up on this factor. You know, maybe there's some feature I can create. If you don't know what feature engineering is, I should look it up. It's really cool. I'm probably right over time. Yeah, all right, and last one is, oh, I have a typo. This should say regime changes. I'll change that. Anyway, so what this can do is it can actually identify changes in temporal patterns or big shifts. So like a great one is like the example they gave in the paper is like the result of the 2008 financial crisis, right? So I'll give an example for me, like when I was working as like, anyway, so I was a business analyst working for a company, and we were in fitness, right? And it was crazy. Like we had the cleanest time series, like model or that data you could ever want. And then COVID hits, right? And we're like a gym, right? So bang, we shut down, right? And then we come out of COVID, and it's like almost impossible. It's so hard to write any good forecast, because not only did we lose a whole bunch of members, had this huge business shift, but demand shifted as people did more digital fitness, right? So like what it effectively did is destroyed our training set because I didn't really have any good data for this post-COVID business environment we worked in. But with TFT, it can actually identify these shifts and still work with it. So, like, to me is incredible. Like I'm so curious like how it does that. I mean, obviously it's somewhere in this really beautiful architecture. But yeah, I think this is just very powerful. Okay, so in conclusion, TFT is an attention-based deep learning model for interpretable high performance multi-horizon forecasting to handle static covariates, known inputs, and observed inputs effectively. We have sequence-to-sequence layers, static encoders, gates, variable selection, and quantile predictions. And really one of the things and then it has very, very novel methods for interpretation, like analyzing important variables, visualizing persistent temporal relationships, and identifying significant regime changes. All right, so hope it made sense. Hope you enjoy it. Have a great day.